Hello, everyone, and welcome. My name is Carmen Guguta, and I'm your host from Technobis Crystallization Systems today. And I have here with me Dr. Priya Pandey. Let me share my screen first, and then we can start. Share. Oh. Wrong button, Priya. Now I think you see my slides, right, Priya?
Yes.
Okay, perfect. So today's webinar is brought to you all by Dr. Priya Pandey, who is now currently a postdoctoral researcher at ULB in Brussels. The webinar today is on investigating polymorphism in molecular semiconductors and fabricating organic field effect transistors. Before we start, I would like to share with you a few, let's say, technical details. The webinar will last about 30 to 45 minutes. We will take questions at the end. Please feel free to use the chat function of this platform to write any question you may have with us, or write directly to us at info@crystallizationsystems.com. After the webinar, also, if you have further questions, please feel free to reach to us either via our website, via this email address, and most probably also directly to Priya. You will see her details shortly. The webinar will be recorded and will be made available tomorrow to you. You will receive an email from where you could watch again the recording, or you could download the slides of that Priya will present today. And with this, for those that do not know, Technobis, we are a company located in the Netherlands, in the north of the Netherlands, with a global reach and presence. So we are selling our product, manufacturing, and marketing our products worldwide. We have two product portfolios, and maybe I go to the next slide. One portfolio on crystallization systems, sorry, and another one newly introduced on the market this April on reaction screening. On reaction screening, the Reactol is our multiple reactor system that comes with automated sampling, quenching and diluting your sample directly into the HPLC vials. It is your instrument for reaction screening, optimization, any type of root scouting, profiling, or kinetics. This is your instrument. But going back to the crystallization portfolio and related to our webinar today, and what also Priya will present today, we have three products in our crystallization portfolio: the Crystal Breeder, Crystal 16, and the Crystal Line. The Crystal Breeder is the multiple reactor systems with 32 reactors working at microliter scale, is your instrument for growing single crystals, coming with quite a lot of gadgets for controlled evaporation, vapor diffusion, sublimation you can do on it. So quite a lot of possibilities to diversify your crystallization screens or growing single crystals. And of course, solvent screening is also possible on it, and some solid state type of screen. The Crystal 16 working in the HPLC vial, 0.5 to 1 milliliter scale. 16 reactors, as the name it says, 4 block temperature blocks, is really your instrument for solubility determination. The temperature dependent solubility curves, metastable zone width, this is your instrument for. Nucleation rate, induction time measurements, phase diagrams, everything you can make with this instrument. Any type of screen, polymorphs, co-crystallization, salt formation, even amorphous solid dispersions. And the crystalline, our third product from the crystallization portfolio, working at slightly larger scale, 2.5 to 5 milliliter scale, comes with the camera technology that works exactly like a microscope. Everything is outside of the vial, nothing is inside in contact with the reactor, the reaction. it is your instrument to use for process development optimization. You get information about particle size distribution, shape, habit. If you have a Raman spectrometer in your lab, you can connect it to this instrument, and you can follow polymorphic transformations or chemical transformations as well with the Raman, how we would do it also in a normal way. And this is it about our instruments. Now I'm happy to introduce to you our presenter today, Dr. Priya Pandey. She, as I mentioned, is a postdoctoral researcher at ULB, currently in Brussels. She did her PhD, her bachelor at West Bengal State University back in 2017, and followed with a master in nanotechnology from the Central University of Gujarat in 2019. From there, she moved for her PhD, where she did it at the University of Bologna with Dr. Enrico Modena from polycrystalline, and under the supervision also of Professor Lucia Maini from the Molecular Crystal Engineering Group in Bologna. Her PhD work focused on the study and characterization of polymorphs of BT derivatives and their application in organic electronics. And the webinar today is also a bit related to her work done during her PhD. And as initially mentioned, after that she followed. She's following a postdoctoral appointment at the Université Libre de Bruxelles in the group of Professor Yves Hertz, exploring polymorphisms of APIs. This is it about Priya. Thank you very much once again for bringing this webinar today and sharing your findings since a little bit ago today with our attendees. I will make you now a presenter, and I think now you can share your slides, and the floor is yours. Thank you very much, Priya.
You. I'll share the slides. Let me know if you can see everything. Just a second. Say something. Okay. Can you see my slides?
Yes, perfect.
Okay, perfect. Thank you, Carmen, for introducing me and giving me this platform to speak today about my PhD work. So today, as she mentioned, that I'm going to mainly present the research of the PhD that I conducted last year. And mainly it was about investigating polymorphism in organic semiconductors and, fabricating organic field effect transistors. And mainly it was done at Polycrystalline, which is a company in Italy, and University of Bologna. So a little bit about the PhD project. So my PhD was a part of this European project, UHMO. And the aim of this project was to gain fundamental understanding of charge transport mechanisms in molecular semiconductors. So there were a lot of early stage researchers, and being one of the ESR, my objective was to perform polymorph screening of molecular semiconductors, perform the structural characterization of each polymorph that we obtain, and optimizing the crystallization processes. And all this was done at the host institutions of PCL and UNIBO. In addition to that, I also had an opportunity to explore the non-equilibrium conditions for like exploring the polymorphisms. So basically, I explored thermal gradient technique at ULB and solution sharing processing and fabrication of OFITs at ICMAP CSIC in Barcelona. So as my topic mainly revolves around polymorphism in organic semiconductors, polymorphism is the ability of a compound to exist in more than one phases, which means that a molecule can pack in more than one packing arrangements. For example, some of the packing arrangements are shown here. I'll just keep it to the pointer. Okay, yeah. So some of the packing arrangements are shown here. And basically, depending on the packing arrangement, a molecular property can be altered significantly. So when we are dealing with organic semiconductors, mainly the key property that we are mainly concerned about is the charge carrier mobility, which can actually alter from one crystal form to another crystal form, that we can see in the next slides when I show some of my results. So as Carmen mentioned, that I mainly worked with the BT-BT derivatives. So this is the BT-BT core, and in the past few decades, there has been a lot of research published with these kind of molecules, which were functionalized mainly at 2 and 7 positions. The reason of this molecule is of selecting this molecule is the viability of the synthetic route and high chemical stability, the solution processibility of this molecule, and the crystal structure packing that leads to a large intermolecular orbital overlap in solid state, which leads to high charge carrier mobility. So when I start the bulk polymer screening, there are several processes that we go through. So the first thing is that we see the solubility screening, which means that we screen the molecule with different solvents, like typically ranging from 25 to 30 solvents, and screen the solvents for its concentration in which the material is getting dissolved in, and followed by the solution crystallization. And after we know which kind of solvents that is soluble in, we can actually vary a lot of conditions for solution crystallization. And one of the techniques I obtained also for solution crystallization was using this crystal 16 from Technobis. Basically, I used this mainly for the crystallization of the compounds that were not very soluble. So I used this to provide the gradient temperature. I could see the clear point, and then I could decrease the temperature and obtain some large crystals through that. Some other methods also include slurry, which doesn't usually give crystals, but at least we can know about the most stable form from this method. Then there is anti-precipitation, which involves adding the anti-solvent to the solution, and we usually obtain precipitates or sometimes crystals. Then there is solvothermal, where we use this kind of autoclave. Basically, this is a high pressure and high temperature technique, and which also gives sometimes large crystals. After, in the end, finally, we have mechanochemistry, where we use the mechanical forces to obtain different polymorphs, or then dissolve it and obtain crystals. So I'll first start with some of the projects, the major projects that I worked on to help you understand how this bulk polymer screening to organic semiconductor and in transistors can be led. So basically, I first started with this molecule of BT-BT that was functionalized at 2 and 7 positions with oligoethylene glycol chain. First, starting with bulk polymer screening, I found 3 polymorphs, 3 crystal forms, I would say, followed by solid state kinetics study using JMAC model, and then establishing the structure and mechanical property relationships. So in the bulk polymorphic study, first we go through is the thermal property characterization. So first, we have to see that how much molecule is stable, then seeing if there is any thermotropic transition. So in this case, you can see form 1, which is a room temperature form, transforms to a high temperature form. And this can be seen from 3 different techniques that we have attempted. Then comes the structural characterization. As I mentioned, the methods of obtaining the crystals, we can obtain crystals and then finally solving them by single crystal XRD. I solved form 1 crystals, and also I obtained form 3, that was a solvate in dichloromethane. If we look at the packing of these 2 polymorphs, I'm sorry, my cursor is moving too fast. If we look at the packing, we see that the BT-BT molecules are arranged in like a herringbone packing motif. And if we look in the overall packing, we can see they are forming layers. While in form 1, they form parallel layers. In form 3, they form anti-parallel layers with solvent molecules intercalated between them. So despite some differences, we found that both these polymorphs are actually quite superimposable. Then there was form 2 that we saw that exists at high temperature. And the problem with sometimes the high temperature polymorphs is that it gets highly disordered, or there are more degree of freedoms at high temperature, due to which we cannot collect the crystal structure using single crystal XRD. But I had the access to the synchrotron, and I collected some high quality powder diffraction data. and used further the JEdit and Topaz. JEdit is basically a Java-based editor, and we can give the commands to Topaz using JEdit, and I could get the indexing of this form. And actually, this was sufficient for me to do the further solid-state kinetic study. So for the solid-state kinetics, basically, I have used the JMAC kinetic model, which is also known as Avrami model. Basically, it describes how a solid transforms from one phase to another phase at a constant temperature. So in the first image, basically, you can see the isotherms at 121 degrees Celsius that we can see from the DSC temperature, where is the transition taking place. And the selected, at a selected temperature, we can see the isotherms, and we can see the form 1 decreasing and form 2 increasing. And this was done using Pong's method. And here you can see an extent of transformation, which follows a typical sigmoidal shape. Basically, the extent of transformation is very slow in the beginning because very few nuclei are there and they are forming or form 2, while it's faster in the middle, where we can see the nuclei that are already formed are growing, and also simultaneously more form 2 is nucleating. And in the end, it's again slow because there remains very less untransformed form 1. And finally, we can see a very slow extent of transformation. So basically, from this, we can use the Avrami equation, and to deduce the Avrami constant. It depends on the nucleation and growth mechanism of the crystal. And for our data, I found that it follows a second order kinetics, which simply means that it is consistent with the nucleation on the surface and one-dimensional growth process. So I was able to do this kind of study because of the collection of the isotherms at the synchrotron, which I acknowledge. And then looking at the structure, we can also see that there is a significant layer separation between the two layers. It can mean that this can act like a facile slip plane, which means that if we try to indent it along the 100 direction, it can bend instead of breaking. I tested it experimentally, and the crystalline remains intact, and it was bending instead of breaking. To get to know the reason of this kind of bending behavior, I also carried out some energy framework analysis. So basically, the tubes you can see, they actually illustrates the extent of energy that is there. So basically, you can see that it forms a 2D network, intraplanar, intralayer, and very less thick tubes are present interlayer, which means that the weakest plane in this case can act like a slip plane, which allows the molecular layers to slide along. So this was like a brief description of this project, and if you are interested, you can also go and read in this paper where you can find more details. Moving on and more going towards the OFIT direction, we also selected some kind of similar molecule in the terms of chain length to see if different chain length or like different functionalization with similar chain length can actually alter the polymorphic behavior or the electrical behavior if we see. So I have selected this C7BTBT. Basically, it is 7 carbon atom long alkyl chain that is functionalized at 2 and 7 positions. From the bulk polymer screening, all the different methods we have tried, I could only find one crystal form. And comparing the crystallographic and packing parameters of C7 with that of the published C8 and C12, we found that actually C7 is isostructural with both these molecules, and there is no such odd even effect that we can see. Further on, moving on with the transfer integrals. So in order to assume that this molecule is a good candidate for making OFITs, we could see it computationally through transfer integrals. And thanks to Dr. Nemo McIntosh from University of Mons, he calculated the transfer integrals. So basically, the transfer integrals of the neighboring molecules indicates the wave function overlap. And the charge transport is expected to be more efficient when the transfer integrals are more balanced in different direction. Here we can see it has like 2D kind of transport characteristics. And if we compare from the literature, it's very similar to the other C8 and C12. So we can expect to have a higher mobility value, just like C8 and C12. So we know that this molecule can be a good candidate for OFITs. So moving towards making the thin films, after trying the conventional methods of making the films, I moved to ULB for a few months to explore the non-equilibrium technique, which is thermal gradient. So in this technique, basically we have two stages, and one stage is called the hot stage, which is set at a temperature which is higher than the melting point of the compound. Then there is other stage that is set at a temperature that is lower than the crystallization temperature of the compound that we know from the DSC, right? And then both these stages are separated by a gap. We put a glass slide on the top, and we put our material sandwiched between two glass cover slips, and then we melt it on the hot stage. After that, we can give a velocity that we want, and then pull the material from hot stage to the cold stage, and we can follow the directional crystallization using the polarized optical microscopy in situ. And this is quite an impressive technique because we can tailor a lot of different different conditions that we can give for the crystallization. So what happens when we use this kind of technique for our molecule is that we can see a nucleation point, and there can be multiple nucleation points that depends on the pulling velocity. Then we can see the crystals are trying to reach the fastest reachable cold end, which is usually in the vertical direction, not always. Then we can see the propagation of the crystals towards the gradient direction. And this whole region, the first ever region in the glass slide, is called the undercooling region. This is where the nucleation takes place, basically. Then comes the alignment and competition region. You can see the crystals are more aligned towards the gradient direction and much cleaner, you can see from there. Basically, this lies in the middle, and where the crystals are in constant where the crystals are in constant competition with each other to reach the growth front faster. In the end, we have the growth and competition region where the growth front has been formed, and we can see much bigger domains of the crystals. And as I mentioned, we can vary a lot of conditions in this kind of technique, like pulling velocity, where we can vary around from 1 micrometer per second to 100 micrometer per second. Cooling rate, the temperature of hot and cold stages, and we can also apply a polymer coating between the substrate and the molecular layer. After trying all these conditions, again, we see that the molecule is stable just in one phase that we obtained in the bulk. Another non-equilibrium technique, or rather I can say deposition technique, I tried was in ICMAP CSIC in Barcelona, where I used a bar-assisted meniscus shearing. As the name suggests, we see a bar and we form a meniscus of our material dissolved in a solvent that it's soluble in. I used chlorobenzene. And then we can shear the material on the top of the silicon wafer by moving it horizontally. Again, we can vary a lot of conditions. We can control these conditions externally and see if it's forming different polymorphs due to tailoring of the conditions, and further we can fabricate the OFITs. So when I use this technique for my molecule, we can see that it's forming quite very homogeneous layers and very isotropic growth. Doing the structural characterization, we can see, again, it's very stable in all the different conditions that we applied, which is actually a good sign for OFITs, because we don't want our transistors to change phases when it's functioning, right? So in the end, I tried to make some OFITs. I tried different configuration, different channel lengths, and different weights of polystyrene using the blend of the C7, and obtained this observation that a blend of my molecule, C7 molecule, with PS of 10,000 gram per mole weight actually has the highest mobility value. And if you see it closely, and in the previous slide, I mentioned the expected mobility value, it actually is quite matching with the expected, and it's very good in terms of the organic molecular semiconductors. So with this molecule, we have reached this fact of obtaining this different kind of transistors and attaining which is the best transistor and condition that we have obtained. And of course, more details are available in this paper that I have mentioned over here. And finally, I would like to talk about one of the other interesting molecule from my point of view. again having the similar kind of chain length, but this time it has a 6-carbon atom alkyl chain, which is capped with a terbutyl bulky group. And exploring the polymorphism, actually, I found that it has 4 kind of different polymorphs. Basically, it can be confusing here that why there is form 1 and why there is form 1A. Form 1 is the starting material, which is obvious, but form 1A, it's recrystallized form 1. Let me explain you why it's written like that. So when we obtained the material as a starting material from ULB, we called it form 1. We recrystallized it, did the powder XRD of the forms, and mainly we obtained the preferentially oriented peaks, which was more or less matching with the powder. But thanks to synchrotron, I obtained a very high quality data and then compared it to the crystal simulated powder XRD and saw that there was slight mismatch, which we thought that it could be due to temperature difference. But again, collecting the same at same temperature, we found that the mismatch persists. We thought it could be due to a bit of transformation or like thermal contraction. Doing a variable temperature XRD actually confirms that there is no phase change or thermal contraction, which means that these two forms, the crystals that was crystallized from form 1 was actually a bit different than the starting material form, although very similar because most of the peaks were still matching. For that, since we already had the crystals of form 1A, I collected them using single crystal XRD and found the unit cell, while form 1 was a powder, which I indexed it using the topaz. And I found that actually these two are 2 different forms, and which was really hard to notice at first, but thanks to the synchrotron data, I could notice the difference in the polymorphs. Then another interesting thing happens. The crystals of form 1A, they are sheet-like. Okay, so basically after half a year of polymorph screening, the stability of this form 1A decreased dramatically because this is not the most stable form at room temperature. The most stable form is form 2 that I will talk about in the next slide. So this is like needles. And I found that due to the unintentional seeding effect of this material, of this form 1A became dramatically unstable. And the solvents, even the crystallization experiments that were yielding form 1A, they no longer yield form 1A, they just give us form 2. And this marks to the disappearing polymorphs. And there's another interesting paper, I think by Dunitz et al., that talks about this kind of disappearing polymorphs, which is quite an interesting read. I would suggest that. Then talking about our most stable form, it's form 2, and that we later found from the slurry experiments. So this molecule, this form actually packs in a very corrugated kind of a manner. And there are 3 molecules in the unit cell. So basically 2 of them are forming herringbone, while the red one, you see, it's a bit shifted that cannot be attributed to a herringbone. We can also see it from the core tilt angle. The two molecules that are forming a herringbone packing motif, they are having the similar core tilt value, while the other one, it's more shifted. This is also a very unusual kind of a packing arrangement that we see usually in the organic semiconductor molecules. In the end, we always have a high temperature polymorph. So I indexed it again using topaz, being it disordered at high temperature. And both form 1A and form 2 crystals, they transform to form 3 at high temperatures. So of course, after all the bulk polymorph conventional screening, I also tried this molecule for finding new polymorphs using non-conventional techniques. And I didn't find a new polymorph, but I did find that it always exists in a mixture of form 1A, 2, and 3, which actually led to a difficulty of fabricating offsets using solution sharing method, for which I turned to my another project colleague, Federico from BSF. So he tried thermal evaporation in high vacuum and tried different kind of conditions. In one of them, we could get some transfer characteristics from where we can extract the mobility values. Not that great, but still we can work with this. And in this case also, we have the same kind of problem that there are 3 polymorphs. These 3 peaks actually are indicating the 3 different polymorphs from 1A, 2, and 3. So to understand why this molecule, while C7 not so different, except for the tert-butyl was having so much good mobility value, or even without the chain, just tert-butyl BTBT is having a good mobility value around 17 units. But this molecule is not working so well. So to understand the reason, another project colleague of mine, Nicholas from University of Strasbourg, he calculated the ionization potential values of different forms, and we could see why this why this molecule is not forming good offits, because of the deep ionization potential values, which means that the injection of the charges will be much more difficult in an offit device with these kind of values. And even the transfer integrals that we have here, they are not the best, because they have 1D transport character, and in this case, they are made of two shifted herringbone planes that can barely exchange any charge. So basically, one thing we can do to make it better of it is that first solving the problem for isolation of the polymorph, because if we solve that problem, at least the mobility value will be a bit enhanced, because different polymorphs will have different grain boundaries that is actually hindering the mobility. Then solving this ionization potential values, maybe blending it with TCNQ or any other work, like any other suggestions that are mainly that people in ICMAB are mainly working on. But until this, I had concluded this project because it was almost ending the PhD. So the basic outlook that I can derive from all the project works that I have performed during the PhD is that to optimize the charge transport and organic field effect transistors, it's very necessary to do a strategic designing of the molecules, and we have to also consider the crystalline engineering and understand all the polymorphs that are present, and that then only we can understand better the relationship between the structure and the electronic properties. So in the end, I would like to acknowledge the UHMOB team of my PhD, my host institutions, the project, and all the collaborators. And of course, this my new postdoc place is ULB. So of course, I acknowledge this lab, and I'll be at your disposal for any kind of questions. That's it.
Thank you very much, Priya.
I think it was quite fast.
Yes. No, but it was really good. Thank you very much, and really interesting this topic, as we were discussing just before the starting to broadcast this webinar. This is quite new topic for our usual attendees. A new adventure for us as technobies, as we also see a bit more demand for our instruments in this field. But maybe in the meantime, you can also share a bit more from your side, because I know you worked and you said about the Crystal 16. What was actually, how do you see that it was? Was it an added value, or let me ask you differently, or how adds up to your work in a positive way, or I see
in
some
a positive way, of course. Yeah, thank you so much. But actually, it was really a positive way, because I used Crystal 16 only when I was not, because some of the materials were not the best when it comes to the solubility. So when I was doing the solubility experiments, normally mostly it was not solubilizing. In some cases it was, but it was very I would say very irregular fashion. So I tried Crystal 16 for that, because then I could see if it's solubilized or not from this clear solution thing in the software. And when I used this gradient temperature, where I could like increase the temperature very gradually and then make it stable for some time, like overnight, and then decrease the temperature gradually, I think this thing actually led me to find some nice big crystals that usually the solution crystallization was not giving such big and separated crystals, So mainly in the case of OEC BTBT and this last one, ditert butyl C6 BTBT, both of the cases, I obtained some big crystals from Crystal 16 actually. So it added, of course.
Yeah, to be sincere, we also hear quite a lot because, of course, the crystal breeder, our instrument crystal breeder, was developed specifically to grow single crystals. So it has also these round bottom vials, the diameter of like the NMR tube, what the crystallographer, a lot of crystallographers will use to grow single crystals. But we hear it quite often from our customers that they also use the crystal 16 for growing nice crystals, good crystals.
And also for slurry, it was quite helpful because then it comes with a stirrer, and
Yes.
you can see it's constant stirring, and it's not evaporating like if you do
Yeah.
in the hot plate. So it actually solves a lot of problems actually.
Yeah. I would like to read one of the questions that comes from Karina Wang. She's saying, thanks for the very interesting talk, Priya. Does any of your BTBT molecule contain color, non-white materials?
Yes, actually, the OEC BTBT, the first project, it was not white. It was colored, I would say, like ochre green.
Okay.
Yeah, so it was colored, but also it was very difficult to solubilize. So it was very soluble in very less solvents because of the OEC chain.
I'm thinking now maybe Karina is asking this because if you have a color compound, depending also on the color of the compound, it is problematic with the transmissivity of the crystal 16. And indeed,
Yeah.
Karina, if you were pointing to this, indeed, not everything is possible. Well, you use the crystal 16 version 2. Now we have a version 3 and also a crystalline. Our newest crystalline, well, not that new anymore, 2 years ago brought on the market. The latest version comes with color camera, so you can do the actually the solubility curves with the information from the cameras. And having a color camera already says quite a lot that and another question for project 3, number 3. Have you ever tried to obtain the high temperature stable polymorph using the technique other than the gradient temperature stage?
Yeah, of course. Yeah. The high temperature, actually, it was stable at high temperature. So basically, if you just treat the form 1 or form 1A or 2 even, just heat them up and you will obtain the high temperature form. The thing is that since it's stable at high temperature, it doesn't become very stable if the powder comes back at a room temperature, basically. So you can see the peaks of form 1A and 2 appearing when you are measuring them at room temperature. And that is the reason that I had to collect the high temperature powder XRDs mainly at synchrotron. Because then when you are heating up and then collecting the XRD, meantime, the peaks of form 1A starts to appear, and that's not like just form 3 then. And yeah, I have obtained the the high temperature form, but only at high temperatures. And when I remove it, there is a mixture.
Okay, thank you. You have quite a few compliments here for the nice talk. Priya, I see it in our chat. I noticed in the beginning there were quite a few people that they experienced some sound problems. I see with Stan, Faraz, Torsten. I'm really sorry about it. I'm not really sure if it is an internet problem. I'm or currently on the road in a hotel room, so I don't know if I was the problem or it's really Zoho, the platform. Now I see that the problem in the comments that is solved. I'm really sorry for this in the beginning, what you have experienced. Please accept our apologies. Nevertheless, as I mentioned, and maybe you didn't hear me in the beginning, this webinar is being recorded, and tomorrow you will be able to rewatch it on our website or on our YouTube channel. You will receive an email from my colleague Irina with all the details on how can you rewatch or download the slides of this webinar. I think when I was talking was the problem. One more question. Hi, Priya. Thank you for the presentation. Did the transmissivity values give indication of change in polymorph? For example, if the transmissivity is increasing, then started to decrease, decreasing. Sometimes indeed you can see it in the transmissivity. You see that one polymorphic form starts to get into solution, but it doesn't go to completion, then it crashes and then again goes into, so you actually measure the solubility of two different forms.
Yeah, actually I didn't have any transmittivity like increase and decrease during the crystallization experiments, because I think the only thing could have appeared was the temperature that I was giving, but I never went until the temperature of the high temperature polymorph. So I didn't observe like multiple polymorphs. I just wanted to have the crystals of the same form. So
yes. Okay. We have one more question. The last question, then we don't go over time. My question is Alu questions is about project free again. So it's quite popular, this project. Yeah. In my opinion, well, in his opinion, we have two different crystal structures, form 1 and form 1A. As shown by the single crystal XRD analysis. It is different to powder XRD pattern samples having preferential orientation on the peaks, generally due to crystallinity. Can you comment on this?
Yes, but I don't understand if it's like a question or...
Yeah, I think it's more like a comment, but do you agree with...
Yeah, it is indeed different, which is, the difference is not that significant actually. So when you collect, as I mentioned, when you collect the powder XRD of the crystals, just to confirm it's the same form as powder or not, you see usually the preferential orientation. So it's very difficult to say that if the crystals that are obtained are always from 1A, or sometimes are also obtained from 1. But the crystal that I chose or selected to do the single crystal XRD, they were a different form, of course. I reproduced this multiple times, but yes, it is different than the powder XRD. Which was only possible to see from the synchrotron data, because there we have less preferential orientation. Even the powder as a starting material, it's crystalline, so it's not very much possible to detect such small changes that are leading to different polymorphs using a conventional, like normal XRD instrument that we always have. So yeah, it is different, and we were lucky to notice it, I would say.
Okay, I think we can stop here. Just let me once again, somebody's thanking you for the wonderful insights into your work, and I would like to also thank you once again, Priya, for sharing this topic, your findings from your PhD with our viewers today, with our attendees, and thank you all. And stay tuned. I think end of August, beginning of September, we come with a new series of webinars. Thank you, Priya. Thank you all. Bye.
Bye.